So, good afternoon, good morning, good afternoon, dear friends. How are you? I apologize. It's very strange this thing about this virus, and all the lessons are messy, and so we have the idea to make some remote lesson on YouTube, okay, in order to gain some time, not to go over the end of the course of the summer. And what about today? What about today? Well, today I wanted to spend in the first video my time talking about another aspect of the linear model, which has an historical name. It is called ANOVA, the analysis of variance. And I explain in a while what is this concept. And after introducing the ANOVA, we will say that we have an, let's say, old-fashioned approach to this problem, but we forget it because we move forward and we discuss in great detail the current approach, which exploit, as you learned in the last lessons, the Akaike information criteria in order to select the best model explaining your data, your response. And we will practice a little on the lab with the R software, or if you prefer with R command, we will see both. And let's say for just to practice I ask please to try to make your best if you have a computer, a PC, or even you will able to do the homework using your mobile phone. So very user friendly. Okay. So what about ANOVA? What is the problem, the initial problem? Do you remember the fresh data set, the data set about concerning my students in medicine, male and female, and we were wondering about their weight, if the weight of a student can be related to his tallness of short height, or with respect to the gender, okay? And please have a look now. This is a couple of box plots, okay? Here you see the situation between girls and boys, the weight measured with respect to the girls and with respect to the boys. The orange are the girls, the purple are the males, okay, and we will see that the box plot are okay. There is a distance between their median, okay. So no surprise, if we perform the t-test, we will find a significant difference. Otherwise, have a look here in another box plot. We see the difference of the weight between the two categories of smokers and not smoker. The orange on the left, not smokers. The brown on the right, smokers. As you see, the box plots are more or less at the same shape, the same position. And if you try to consider the t-test, the linear model, asking to be the smoke as a covariate, as a predictor, and the weight on the y-axis as the response, you will not find any significant p-value, okay? And we will check for it with the software in a while. Okay, it is easy to perform the t-test from the algebraic point of view. Why? Have a look just to the standard, the formula, the t, the statistic, the test statistics. It's just a difference, do you remember? The difference between the means over this signal-to-noise ratio, which is sigma over the square root of n, which is the standard error of the standard error of the mean, okay? Now, if you reflect, how can we modify this sort of test statistic if we have not two groups, but three. Have a look. If you reflect here below on the denominator, it's not a problem. You can add another term plus sigma squared over n, sigma 3 squared over n 3. So this is easy. But above, on the fraction, well, we cannot do nothing because we have not, there is no sense. Let's say media 1 minus, mean 1 minus mean 2 minus mean 3. What does it mean? What does it mean, the mean? Nothing, okay, you cannot do it. So there is a trick, We can not perform the t-test if we have 3 or more groups. So this is a big issue, which is the escape way. Please have a look here to this join 2 box plot. You see on the left here the difference in weight between the boys and girls. Okay, there is a displacement. There is a difference between the average, the median. But also you see that the boxes are, in a sense, reduced, smaller. On the contrary, there, when you consider the smoke, the boxes are, in a sense, at the same position, but also they are wider, the interquartile range. The boxes are wider, okay? This is the trick, this is the clever trick. To consider not difference between means when you have 3 groups, but difference between variances, between standard deviations, okay? Not reflecting on the position, but on the heterogeneity, the variability. This is the idea. So as an example, let us consider the physical activity. We say gym, okay? We classify our students into 3 groups. Those who not practice sport, in a sense, nothing or little, very few activity. And the second group, this purple, and this orange is the group in a sense occasional, okay, sometimes. And the last, the brown group, is yes, we are sporty, very very active in gym and sport activity. Okay, so it seems that the purple box, in a sense, has a weight greater than the other 2 groups. Okay, and we want to investigate about it. Okay, so not with the t-test, not with the t-test. Now let me move to R, or to R commander, in order to show that if we we put a relation, the weight till the gym, the physical activity, and we perform the linear model computation, we obtain for sure a significant p-value, which means that okay, there is a difference. A group, 1 or more groups, are different from 1 or other groups, but we don't know which is which and who is who. And so we have a little problem now, because we have to detect when in which way we can decide that the second, for instance, the second and the third group is different from the first, but they are in a sense equivalent. Is this true or not? Well, this is in a classical approach is called a multiple comparison issue. And there are a lot of books, a lot of papers, and many tools and tricks to afford this problem, actually. And I say the situation really is tricky and hard and confusing and puzzling. And when you put some, for instance, you make some research, you wait for the response of the referee. No, do you perform the check of the multiple? Do you perform the Bonferroni correction? Do you check for heteroscedastis? Many issues, many details. Very dangerous thing. And if you go, I refer you please to the book. If you wanted to know some details about it. Otherwise, if you choose the Akaike information criteria approach, well, everything is really simpler. Okay. How? In which way? Well, but really, it is sufficient to recode the information. Let's say we have three groups. Okay, we have the groups not, and the group O, occasional, and the group S, sporty. Okay, you can try to join, for instance, the first and the second group, or the second and the third, or the first and the third. Okay, you can try to make some. Let's say, let's try some, and you perform a linear model, and again you go to see which model possess the lowest Akaike information criteria. That is the model. That is the model to describe properly the situation. I will show you in a while. I will do it both with the R commander and both with R. Okay. So let's move to the console. Okay. I open my computer.
So here we are. Let's suppose to have here the fresh dataset on your desktop already downloaded, and let's call the R commander. Now, you remember with the data import data menu from text file, we ask that the field separator is the comma, okay, and we search on the desk, double click the desk, the fresh CSV dataset. Okay, we have 60 rows and 10 columns. Let's have a look. View the dataset. Here we have it. Okay, and now let's go to the menu Statistics, Means, and one-way analysis of variance. Here we have the, let's say, the old-fashioned approach to the analysis of difference between means within many groups. One way means that you have one input, one covariate, and the response is the numerical data of the weight of our students. So we click one way ANOVA, we ask for the group, which is gym, you remember, and the weight is the response. If you try to compute OK, you obtain here a p-value, a significant p-value, which is to say that, okay, there is some difference. Some group is different from some other, but we don't know really which is the group different from the other. For instance, okay, we are quite sure that the students not having sport activity has a weight, okay, greater than the other. But it's difficult for us to decide if the other two, occasional and sporty, are different. Do you remember let's have a, do you remember the box plot? This box plot, okay. It's we are quite sure that the purple are have a weight greater than the other two, but it's different. It is difficult to say if orange and brown are different, okay? So the classical approach is, let's recompute again the ANOVA. So statistics means one-way ANOVA, gym, okay, weight the response, click here, pairwise comparison of means. What does it mean? It means that we check by means of a sort of t-test whether the purple and the orange are different, not and occasional. Are different? Well, occasional and not. Here you see a confidence interval, a 95 confidence interval, according a specialty test, which is called a honest significant difference test. It was provided by the legendary statistician John Wilder Tukey. Okay, and we are sure that the purple and the orange are different because the confidence interval do not overlap the border of the zero. Okay, so this statistic, approximately -10, is very far away from zero, and so purple and orange are for sure different, have different weight. Okay, well, we are quite confident also that the sporty and the occasional, I say the brown and the orange, are not different, because this test statistic, more or less free, is not far away from zero. The 95 confidence interval overlap the border zero. Okay, so orange and brown are not different. Now the question, again, the difficult question, is to decide whether purple and brown are or not different. Okay, because you see, the 95 family-wise confidence level interval in effect overlap zero, and this is a very, very tricky situation. Okay, if you look in detail here, okay, we ask, does the difference in mean between sporty and not is or not equal to zero? Well, the 95% confidence interval spans from -12 to 0.2. Okay, very difficult to decide. So best thing to do is not to exploit the one-way ANOVA, but to fit the model, according to the linear model. I prefer to show you not using the R commander, but I prefer to use R. So let's rearrange again the thing. Okay, move on R. Here we have it. This is R. Let's start a new script, new document here. So I try to import to read according to the CSV format file dot choose open closed data set with a header equal true, and I call it fresher. So and I attach fresher and look to it. Look to the tail, the last 6 rows. Run on the desk. I have that fresher CSV file, and here we have, and here we let me arrange here data. Okay, so I prefer to put it this way. Just 1 minute. Okay, let's show again that. Okay, better. So we are interested in studying the weight of our student. We can, of course, have some descriptive statistic till the 1. This is the null model. Model 0 equal linear model, okay, and performing a summary of this model 0. Do you remember? We obtain the mean 63 kilos, okay, the precision 1.9 of this estimate, okay, and so stop, okay, and this is the standard deviation of the weight of our students, okay. So we are interested in studying the model 1, I say, which is, can I explain the weight according to the gym activity? And I ask for the summary of model 1. Well, actually, not only the summary, but also the information provided by this model, the Akaike information criteria. Model 1, okay, run. And again, we find those estimates provided also by our command. 69 for the purple, 69 kilos for the purple, 69 minus 9, which is 60 for the orange, occasional, 60, and 69 minus 6, which is 63, for the brown, for the sport, okay, 63, okay, here. Good. But we want to decide, do you remember, if the brown are different from the purple in another, in other terms. The brown are similar to the purple and different from the orange, or the brown are similar to the orange and different from the purple? This is the question. So we proceed by attempt. Let's make a first try. We consider, for instance, to put together orange and brown. Okay, so have a look. I create a copy of the variable gym and I call it gym OS. Gym OS equal gym. Let's check. Gym and gym OS are the same object, of course. Okay, they are the same object, repeated again, which is just a photocopy. Okay, now I act on the levels. Which are the levels of GMOS? Which are the levels of GMOS? So, they are not occasional and sporty like gym, of course. Well, now I ask, Who is the third level of GymOS? Who is it? Well, it is Sporty. Okay, I change its name. I use another name. I use a fantasy name. Say I don't know, Sporty Occasional. Sport Spurt Okay. I try to do this, and I ask now, who is the third level? It is not anymore sporty. It is sport ok. Okay. Have a look. Now, GymOS is not occasional and sport ok. Okay. Now the trick is to call also the second level with the same name. Okay. The trick is to call the second level with the same name. Okay. So GymOS now currently has not anymore 1, 2, 3 levels like the started gym variability, but only the 2 levels, not and sport ok. Have a look. If you if you ask to depict the situation, wait till the GymOS, you obtain only 2 box plot because the orange, have a look, the orange and the brown has melted together. Okay, these are the purple, the original, but the second and third group has melted into only one super group, which is called Sport OCC. Okay, Sport Occasional altogether. So we are going to investigate over this other model. So we consider the model 1. We consider the model 1 and we modify it, calling the model 2 GymOS model 2, and have a look to the summary, but more quickly to the Akaike information criteria, model 1, model 2. So model 2, here we have the model 2, the weight according to the 2 new group, the purple, the nut, and the other 2. Okay, and this is the summary, the p-value, and okay. But more important here, what you say that by means of this choice, that you obtain a lower entropy, a lower Akaike information criteria. So that model 2 is better than model 1. Okay, and if you try to perform the same analysis, putting the brown sporty group with the purple nut, and you test this junior group versus the occasional, you will check that the Akaike information criteria is not so low. So we have discovered the correct, the true situation. The true situation is this one. We have the purple, the knot group, which is different from the 2 other groups, the sporty and the occasional. But the 2 groups, the brown and the orange, are the same, can be melted together. And this is the minimal adequate model according to the ANOVA analysis. Very, very interesting. Good. So let's conclude our strange lessons, okay? We have talked about the ANOVA, the analysis of variance, which is a technique to detect difference between many groups. Difference in means, of course. It is nothing but a linear model. And we select the best linear model exploiting the Akaike information criteria, which is to select the model which has the smallest entropy of information. Okay, now let's try to do your homework. Okay, I choose a simple example. Look above the iris data set. Okay, do you remember those setosa, versicolor, and virginica flowers? And you are required to detect if the width of their sepal is different within the groups, and which groups are different from the other. Okay, an ANOVA linear model. Well, you can use, of course, R and R commander. It's very simple, and but provided that you do not have a computer, you can do it also in your room at your home. Okay, just exploiting the phone, because if you go to this rdrr.io, I have it also this, you got rdrr.io, and run code online. If you ask to run code online, you can simply attach iris dataset and simply perform the same calculation you do with R. It's just a little messy because you have to pick the commands okay, with your finger, but in case of emergency you also have R on your mobile phone. Okay, very useful, of course. Okay? So let's hope to see you again within the ICTP laboratories next week. Okay, I'll see you. Bye.